Alexei, Jan, and Ren for organizing this workshop and inviting me to come here. When I saw the title of the workshop, Simulation in Complex Porous Media, I said, what I'm doing that is so complex? I'm actually nothing. But lately, I've been collaborating with Gabriele Chiogna and Olaf Tjurka, looking at mixing in something that we call complex groundwater flow topology. So that's what I'm going to present today. So first, I would like to introduce this subject, looking at geological formations. We're mostly interested with my co-authors in groundwater hydrology. So we think in these formations and the classical simple model of an aquifer, a multi-layer aquifer, right? Where even if we don't know much about geology, we can see that there are different units here, something that we call hydrogeological units. And that we see at the kilometer scale, we can also observe it at the meter scale. So typically, to deal with that kind of heterogeneity, if we don't want to represent it completely, we just go and upscale this in a simple way. This is just saturated flow modeling. What we come up is with effective hydraulic conductivity, for example, that is anisotropic. And when I show this in my groundwater class, the students always ask me, okay, how much the anisotropy, right? And I don't know if we have an answer, but the rule of thumb that everyone uses is that vertical direction is approximately 10 to 100 times less than the horizontal direction. So that's for that kind of scale, and that is accepted. We use it like that in groundwater modeling, etc. However, recently, some people have looked at very detailed experiments. This is a sample of rock. Here you have the dimension. This is a 30 by 30 centimeter by 2 centimeter thick. And they did some very detailed experiments. They used a gas permeameter and sampled almost 9,000 points in this area, looking at the values of permeability. What they found is that even at that very small scale, you also have this kind of layering in the properties in hydraulic conductivity or permeability and also in porosity, which means that even at that scale, probably the right thing to do is to consider that these properties are anisotropic. So thinking on that, then we went and we start playing with this very simple model. It's a two-layer model where in the second layer, you only have isotropic hydraulic conductivity, only the main components of the tensor. But in the first layer, you assume that this is anisotropic, and given that the principal axes are rotated with respect to this coordinate system, you get some off-diagonal term. And in this case, we are only considering the case of the xy plane here. So, and we impose very simple. I told you I'm not working with very complex things. This is very simple. It's just no flow boundary conditions. And this boundary, the lower one, and this one. And then we assume that it is a constant hydraulic gradient in this direction. And when you do that, other people have done it before. And of course, I have to, just to remind, everyone here knows this, but if we take this coordinate system, xy, and then we have that this red one represents the principal axis of the hydraulic conductivity, and we have a rotational angle beta there, then we have that these relations here apply. And we will define this ratio here as R is a ratio between the main components of the hydraulic conductivity in layer 1. So some people have worked with this, and they found that you can get an analytical solution for the flow field that comes out of that problem. And it's a nice paper, this one in 2004 by Bergen and Hemker. So we use this analytical flow field, compute it, and when you compute it, I apologize for the quality here of the images, what you get is that these lines, these yellow lines there show the streamlines that come up out of that field. So you have this helical flow field that comes out of that very simple flow model. So the colors here show, in this case, the total velocity magnitude of total velocity. And here you have the x component, where you see that is larger out of the center of the domain. And then if you look at the other components of the velocity, you observe that they have some distribution that, of course, is related to this helical motion that we are getting there. So when you look at this, it's difficult to think how complex can become the problem with when you insert solute here and you want to look at the mixing. So for that, I would show some simple example. So I have some animations here. So here, what I'm showing is you have two small particle clusters. You have a lot of particles there. And we just show how they travel in this flow field. So the red one is at the center of the domain, and the yellow one is a little bit farther out to the boundaries. So what you observe, and here I want to highlight this one. What you observe there is that these things that start as a perfect sphere now is stretching, and it's becoming like a filament there. And as it goes, it stretches more and more. And while the red one, it seems that after a while, it doesn't change much in the shape. And I will show you another animation that shows this from a different perspective. So now we are looking at this from the injection plane. We're looking at the direction of the flow. And when we let this to go, it looks a little bit like a galaxy in the middle. But what's showing there is the deformation. So the deformation of this yellow sphere there is mostly due to stretching. As it moves, you get the stretches, becomes longer, while this one at the center mostly folds. So we have two different mechanisms, stretching in the yellow one and folding that is in the center. So now this is in a kind of 2D image. And here is another one just to give you another sense. So this is the whole injection plane that we have here. And when you start looking at this interface that are marked by these spheres of the same point, the points of the same color, you see that here this interface, it gets longer. Eventually, that has big implications for mixing, as I will discuss later. So I will just let the animation there. So it seems that everything gets mixed in this case, and that is a 2D perspective. But then if you look also in 3D, and here I don't know if you will see, but you will see that there are some particles that travel faster in the x direction, plus this rotational motion in the other side. So the problem is essentially it's a 3D problem, and we wanted to see how that can impact solute mixing. And we were looking at this not only for applications in groundwater, but we also see that could have a potential application in chemical mixers, for example, for the design of that kind of things. So there is quite a few papers about this topic, mostly by Herrera, but also there is one by Theis, 1967, that already discussed this potential helical motion in anisotropic porous media. So our objective now is to extend this and quantify the effect of complex flow topology on transport processes to numerical simulations, and that's what I show next. So just a little bit of introduction. When we talk about solute mixing, and here I'm talking not the pore-scale, I'm talking a Darcy scale, right? When we have a solid plume, something that usually when we talk about stochastic hydrogeology, we think that heterogeneities generate these kind of random interfaces here. So if we make a zoom out of this, and we have some water that has some solute that is red, and some water without solute, that is in blue. Then we have an interface, sharp interface between both of them if we don't add some kind of mixing at the pore scale. If we add mixing at the pore scale, usually we do it through local dispersion, then we will have this kind of interface here, this zone of mixing that is shown in green color. So mixing is due to these two mechanisms. The larger this interface that we have here, the larger is the mass exchange between these two regions, so we have more mixing, and also it depends on the value of this local dispersion. So to look at this problem from a numerical point of view is quite challenging because the flow had this strange shape, or this difficult shape. So we're using some numerical method developed by us, which we call a hybrid streamline-SPH. Essentially what we do is we trace the streamlines and we discretize the streamlines with some numerical nodes, such as we can solve advection almost exactly along the streamlines and also longitudinal dispersion. And then we use some kind of meshless method to come up with some terms to account for transverse dispersion. So that is very accurate numerical method for this kind of problem, because we can also do the trick to just simulate the effect of longitudinal dispersion and then add transverse dispersion to see if it makes some difference. And we will see that it makes it. So so when we do that, we start working with a coordinate system that is oriented with the flow. So we have a grid that is oriented with the flow, and then we solve, and we use an operator splitting approach, and we solve two terms, one of advection and another one with dispersion, and eventually reactions. So we did a test problem with this dimension, x, the length, 30 meters, width 4 meters, 2 meters. To get a nice description of the velocity field, we have to use 12 million cells just for the flow field. Then we trace 3,200 streamlines. No? Oh, we just went to the one of the first slides with this equation, This equation. And we assume these parameters just to start. Oh, these parameters are here. We just assume that in layer 1, you have one off-diagonal term that has that value. Yeah, the first layer, there are two homogeneous layers. That is true, that is very important. There is no heterogeneity more than that, 2 layers. And they have the same diagonal terms in the hydraulic conductivity, and only these off-diagonal terms will account for anisotropy in the first layer. So very simple. And then we use these equations. Sorry? Yeah, that's analytical, but you need to evaluate it in some numerical grid. The solution is this one. It's exact. It's exact. So yeah, that's the point. And the flow field is computed through this analytical expression. But then you need to map it onto a numerical grid for the computation. And for that grid, we use 12 million cells just to get a nice description for the problem that we were simulating.
One quick question. For the case where the density is constant, when you have incompressible flow, then the streamlines are static, they are fixed in space. But for instance, when you have gas flow, compressible flow, then they have a change because of the change in densities. So this is going to be restricted to incompressible flow?
For now, we're working with the steady-state flow, assuming that the streamlines are constant, they don't change, they're fixed. Eventually, you can also use this method, but you have to retrace the streamlines each time, and then you need to somehow interpolate your previous values, which will add some kind of numerical error, but it's possible, it's doable. But that's one of the main disadvantages of this kind of method. But for this problem, as it is, it's...
You almost never have an analytical solution. Never have an analytical solution because of transient flow. Only one is
Yeah, no, that's why I say it's simple in the sense that it's a state flow, saturated flow, conservative solid, as I will show. It's very simple in that. The only thing that is complex is the flow field, or somehow complex. Maybe it's too simple, but.
Coming back to this, so the original system was with no diffusion.
Yeah, no, this is only the flow field.
The flow field is.
The flow field is there, and it gives you these helical streamlines. Yeah, so the different components. Well, this is the component of the velocity in layer 1, in the x direction, in the y direction, layer 2.
So no singularity.
No, and then at the interface you have this. At the interface you have this BZ. No, they have to be. There is some kind of difference there in BX, but BC, in the vertical direction, it has to be continuous there. That is a good question.
But what I'm talking about, if you have discontinuity in velocity, then you don't have a uniqueness for the Lagrangian projector. The Lagrangian projector can split.
Mm-hmm.
You can easily show example, and if the velocity is not differentiable, you don't have a unique Lagrangian projector. It's spontaneous stochasticity.
Mm-hmm.
Lagrangian projector.
Yeah. No.
The trajectory splits in finite time.
Mm-hmm.
Start with the same initial condition.
You have some kind of chaotic system, right? It's like what happened at pore-scale. There's a nice paper.
Like this continuity here will be a very particular one, right? Because you have the divergence of the flow field is equal to 0.
Yeah.
Probably it's okay.
So probably it's okay because any discontinuity will only be not in the parallel to the flow. It will be tangential to the velocity vector.
In the sense that you have a uniqueness on both sides, so you should put the rule together.
I mean, this has non-zero helicity.
Because usually
For sure.
what happens in non-uniqueness happens when you have it's not just discontinuity of the set of the derivative. There is a it's a singularity something x power alpha. If the speed is not jumping, the speed is not derivative of speed not jumping, but it makes some cusp.
Mm-hmm.
Then you have.
Yeah. Now, I don't know if by looking at this animation we can somehow answer the question, because your question was that if you look at what happened here at the interface, because this is centered at the domain, then you will see here there is some kind of difference, horizontal velocity there at the interface. That's why it produces that. There's a shear that generates that kind of folding. So we did that, and then we compute a very simple example, a black kind of initial condition. So we have a concentration C0, and this here, and then we simulate this sometime later, and then, well, this stuff starts diluting just because of different speeds, right? So solid will move faster in some streamlines, and then if you add, for example, transfer dispersion, you will have transfer of mass between fast streamlines and slow streamlines. And then you can also look what is the concentration distribution along each streamline. And we did it for 0 transfer dispersion, so there is no transfer dispersion, and you get this kind of shape of the curve, something that we were talking in the previous talk. While when you add transfer dispersion, then you are getting this kind of non-symmetric shape of the concentration distribution. And if you look, this is the concentration along a streamline, but you can also get the breakthrough curve, and you also get this kind of asymmetry in the distribution there. So this indicates that transfer dispersion is very important, at least for the shape of your concentration distribution. But we say Okay, let's look at another streamline, and if you look at another streamline, there is no difference at all. So it doesn't seem like a very formal way to look at this. So then we say, okay, this looks interesting, but we need to take another approach. And the question that we wanted to ask are, what are the mechanisms that explain solid mixing induced by the flow topology? What is the main magnitude of the influence? What are the most relevant parameters that control the flow field and solid transport? So for that, we use, again, the same setting. We only use a longer domain. But then we did a full set of simulations looking at different anisotropy ratios and different angles of the rotation. So we got this table here. And we use a method to somehow compute what is the deformation of the flow induced by the flow field. So the method is based on this idea. We put a cluster of particles with one central particle here. At the beginning, they are all at the same distance from the central particle. And then as the flow moves, right, you get deformation. If all particles move with the same velocity, then you won't get any deformation. And then there are these two expressions here that one is related to stretching, which is related to linear deformation, and this other one here that is folding is nonlinear deformation. And here there is a term that is matrix A that is computed in a way that minimizes this folding there. That is the way that is computed. So this is the only, I would say, a little bit more complicated step in this calculation is to compute this A. That means to use a least square method to compute it. And it's very well explained in these two references there. So we did that. And to do that then, we went to the initial injection plane, and we put 629 particle clusters to cover the whole injection plane. Each cluster has 100 particles. So now we can get how much folding and stretching is in each streamline, in these 629 streamlines that crosses these initial spheres there. So what they show this figure here is for some time, we went and compute the ratio between, the logarithm of the ratio between folding and stretching. So red colors here, you have more folding than stretching. Blue colors, you have more stretching than folding. And we went and projected onto the initial injection plane. So what you see here is that depending on the angle beta and the anisotropy ratio that is given by this value of the off-diagonal term, you get different kind of shape where you have more helicity or higher rotational velocity in some cases and in the other ones. For example, in this one here, you still have only one arm, while in this here, you have the arms are a lot more developed. So then we went and we say, okay, let's now compute what is the ratio between the spheres or the particle clusters that have higher folding than stretching. And at the beginning, for different angles beta and for different anisotropy ratios. And at the beginning, and this is versus time, at the beginning, they all have more or less the same. And that is because all is controlled by the spheres that are at the interface. That all is happening there. But if you wait longer, you start seeing that there are differences. And that, for example, for all the lines that are 45 degrees, the one here, you see that this light blue here, you have less folding in relative terms. That for this line here, the orange one, where you have higher anisotropy. So higher anisotropy generates more folding. That is the idea in relative terms. And that's why we were quantifying there.
Just a quick question about this folding and stretching. Is it meaningful to directly compare the magnitude of DNA? Are they somehow in units where it's, is the inequality here sensible, or can you multiply by a factor 2? Is D greater than 2 times A?
That is a very good question. Let's go to the definition of here you have the same unit. So
the same unit, but
there's
no reason why you couldn't add a factor 2.
yeah. Yeah, that's correct. But in relative terms, still, you have some areas of the flow where folding is more important than in other areas.
Yeah.
All right. So, and then when we saw that, then we wanted to answer this other question that is related with this dilution, or the dilution index. And what's the idea of the dilution index is initially you have some mass that is occupying some volume at T0. And as you get more dilution, this mass is occupying a larger volume. And to quantify that, Kitanides, 1994, proposed to use this dilution index that is defined first with this concentration density. You take the concentration at some point, and you divide it by the mass, and then you integrate that over the whole domain, and you take the exponential of that, and that defines this dilution index. And that's a little bit of entropy, right? And then this dilution index has a maximum value, that is when the total mass is occupying the whole domain of the simulation. That is the maximum dilution that you can get. So the reaction ratio is this dilution index divided by the total volume of the domain. So you go to the maximum value. So, and then what we did is we simulate two spheres, one starting at the center of the domain, another one a little bit out to the boundary. And we did it for different anisotropy ratios. So this is sphere 1 is the orange one, sphere 2 is the blue one here. And if you look at the sphere 2, you see that this reaction ratio is higher for the one with the higher anisotropy ratio. So that means higher anisotropy, you get more dilution. That's why it's showing essentially this thing. And that is considered transfer dispersion. But if you don't consider transfer dispersion, then you don't get any difference between the different cases. So that means all the dilution here is induced by this transfer dispersion. And some question that I don't know the answer really, but how you measure transfer dispersion in porous media? Transfer dispersion. We know how to use the typical way to measure longitudinal dispersion is breakthrough in columns, right? But how do you measure transfer dispersion? Yeah, I mean, one way that people have done it is you have a small source, and then you see, and you get a state, and the plume gets longer, but it's pretty difficult to measure directly, right? And there is also some people, like my co-authors, don't think that transfer dispersion actually is different for different components, that you really need to take into account that kind of things. So this is showing that at least for this kind of flow field, it's very important what is the value that you're using for transfer dispersion. Okay, this one here is showing for the same anisotropy ratio for different angles of rotation. And what you get is essentially for sphere 1, for sphere 1, that is the one here, you see that there is no difference in dilution, almost no difference in dilution for the different cases. And that is because that sphere is controlled completely by this churning that occurs between the interface of the two layers. While for sphere 2, that is outside, still there is a difference here in the dilution that you get.
How would it depend on the size of the sphere?
Hmm?
How would it depend on the size of the sphere?
Yes, you would expect that if the size is too large, right, you will be in the middle between both of them, because this that you're observing here for this kind of a sphere, you should see it if you're using a larger sphere. Yeah. Again. Yeah. Again, what is the purpose behind this? That it doesn't seem very like. Is to say if you would design a mixer that is based in this kind of anisotropy, where would you put the input in order to get more mixing inside the mixer? That is the idea a little bit. Yeah. So what are the conclusions? Natural porous media are in general anisotropic. Herrera continuity must be represented as a tensor. Complex 3D flow topologies may arise in simple settings. And this is something that we did. I work with Olaf and Gabriele in the numerical part, but they have done experiments where they have recreated these helical streamlines. In such complex flows, stretching and folding are greatly enhanced with respect to the more traditional flow fields. In the few situations analyzed, even a small variations in transverse dispersion produce large differences in the concentration distribution, and streamline simulations are useful for analyzing this kind of flow fields. So with that, I finished. I was very brief. So yes. Just to mention one thing, I think it would be a very good idea to keep the tradition about this workshop and make it a tradition. So next time maybe we can make it in Santiago. So